For the summary, styrene, also known as vinyl benzene, is most commonly produced by catalytic dehydrogenation of alkylbenzene and used in the chemical industry as an important monomer that can bond together to make polystyrene.
50 kmol per hour C8H8 is used as original basis before convert to mol per hour, and the conversion at B is 78% is given for this process. In material balance, the oxidative hydrogen is removed during the dehydrogenation of ethylbenzene to avoid explosion. After cooling and condensation steps have been carried out, the ethylbenzene is recycled to the reactor preheater and the styrene is taken off as product. For energy balance, the temperature that used from T1 until T11 are 27, 28, 500, 700, 600, 540, 27, 27, 27, 27, and 27 degrees Celsius. Then, each unit has their own reference state. After having worked on catalytic dehydrogenation reaction in steam, it appeared that these reactions show many parallels. Carbon deposit formation on the catalyst is closely connected to all dehydrogenation reactions of ethylbenzene to styrene. They always go hand in hand and cannot be separated. Besides that, in order to achieve this goal, all these processes need to be properly understood.
Fresh ethylbenzene is heated from 28 degrees Celsius to 525 degrees Celsius at A, and the heated ethylbenzene is mixed with steam at 725 degrees Celsius to produce the feed to the reactor B at 625 degrees Celsius. The steam suppresses an undesired side reaction and removes carbon deposited on the catalyst surface. In A, only ethylbenzene will enter the heating vent and only heating process occurs in the equipment. So, the product that will produce in the heating vent remain the same, which is ethylbenzene. A once through conversion at the reactor of 83% is achieved in the reactor B, and the product emerges at 585 degrees Celsius. Amount of ethylbenzene from A is 47293.06 mole ethylbenzene per hour. So, based on 2:1 ratio, molar flow rate of H2O that entered the reactor B is 23646.53 mole water per hour. From stoichiometry equation, 1 mole of C8H8 that form will produce 1 mole of H2. The product stream is cooled to 28 degrees Celsius at C, condensing essentially all of the water, ethylbenzene and styrene, and allowing hydrogen to pass out as recoverable byproduct of the process at 31 degrees Celsius. For H2, H2 is flamed out to avoid explosion at hydrogen aldehyde. That is why mole fraction of hydrogen gas is 1.0 mole per mole total.
The water and hydrocarbon liquids are immiscible and separated in a settling tank decanter T. The molar flow rate of H2O at settling tank decanter is 24119.43 mole per hour, and the mole fraction is 1.0 mole per mole total, and only H2O flow from this outstream and go to E. The water at 29 degrees C is vaporized and heated at E to produce the steam that mixes with the ethyl benzene feed to the reactor. The hydrocarbon stream leaving the decanter at 30 degrees C is fed to a distillation tower. So, for the material balance at E, there is no reaction for water here. Only heating occurred at E. A distillation tower F, which separates the mixture into essentially pure styrene and ethyl benzene, each at 32 degrees C and 28 degrees C. After cooling and condensation steps have been carried out, the ethyl benzene is recycled to the reactor preheater and the styrene is taken off as a product. The molar flow rate for styrene is 36519.65 mol per hour and for the ethyl benzene is 10,300.42 mol per hour. The molar fraction is 1.0 per mole total for styrene and ethyl benzene.
Heater is one of the equipment that we use in this process. Process heater is a direct heat exchanger that uses the hot gases of combustion to raise the temperature of a feed flowing through coils of tube aligned throughout the heater. As we want to produce styrene through conversion of ethyl benzene, the substance ethyl benzene need to enter this heater with temperature 28 degrees Celsius and heated until vaporized to 525 degrees Celsius. Process heaters are used throughout the hydrocarbon and chemical processing industries in places such as refineries, gas plants, and petrochemicals. We use reactors in this process. Chemical reactors are vessels designed to contain chemical reactions. The design of a chemical reactor deals with multiple aspects of chemical engineering. Chemical engineers design reactors to maximize net present value for the given reaction. In this reactor, water and ethyl benzene entered and reaction is occurred. The product of this reaction is styrene, ethyl benzene, water and hydrogen gas. Then, we use condenser in this process. Condenser is a device or unit used to condense a substance from its gaseous state to liquid state, typically by cooling it. Condensers are typically heat exchangers which have various designs and come in many sizes ranging from rather small handheld to very large industrial scale units used in plant processes.
Decanter is a process for high rotational speed to separate components of different density. It is maybe either to produce a clean decant or to remove undesired liquid from the other layer. In this process, settling tank decanters are used to separate water and hydrocarbon liquids where there is a sufficient difference density. In an operating decanter, there will be a heavy liquid separating dispersed liquid and clear light liquid. Boiler is used heat to convert water into steam for variety of applications. Steam boiler also has a closed vessel where water or other substances is heated. Steam or vapor generated and steam is superheated. Water tube boiler in this process is heated inside tube and hot gases surrounded these tubes. Distillation column is an equipment that able to separate liquid by means of relativity volatility differences. Lighter component will tend to concentrate on vapor gas. Heavy component will tend to concentrate in liquid phase. In this process, hydrocarbon stream leaving the decanter is fed to distillation tower to separate the mixture into pure styrene and ethyl benzene. Under the factor equipment design, the equipment that has been chosen is condenser and plate type. For condenser, condensation on the shell side is preferred since there is less subcooling of condensate and a lower pressure drop is required. This is important factors in vacuum lattice. Furthermore, with cooling water on the shell side, any fouling can be removed more easily. On the other hand, tube side condensation can be more advantageous whenever process fluid characteristics dictate the use of more expensive exotic materials. Capital cost of the unit can be reduced by using a carbon steel shell. For plate type, there are three main types such as sieve tray, bubble cap, and valve tray. We have selected sieve tray because they are lighter in weight and less expensive. Besides that, it is easier and cheaper to install. Peak efficiency is generally high and maintenance cost is reduced due to the ease of cleaning. It is also possible to increase the flexibility of a sieve tray for occasional load throughout operation by maintaining a high vapor boil-up and increasing the reflux ratio.
Under the factor for material design, the unit operation that has been chosen is distillation column. For the wall column material, carbon steel has been chosen as our material for distillation column design. Carbon and iron is the main alloying constituent. Carbon steel is one of the strongest, most durable and popular metal alloy. Next, for the pipe material, stainless steel are chosen for the material of the pipe. This is because stainless steel can resist the corrosion and oxidation. Other than that, this type of steel also can resist the high temperature and low maintenance costs. It also can maintain the purity of material which come in contact with the stainless steel. The stainless steel also able to resist the corrosion by the addition of a minimum of 12% chromium to the iron alloy.